Hello everyone, this is Dr. Webb, and here we are. This is the big one. The culmination of all of our work through this term. In this video, we are going to be proving the fundamental theorem of Galois theory. So this is where we're putting together all the pieces that we've been working on through this semester and piecing them all together to make one big, glorious picture. Before we go into the statement of the final theorem, of the fundamental theorem, let's go back through and review some of the important definitions and results that we've gone over this term. So first, just recall definition of a Galois group. For a field extension L over K, the Galois group of L over K is the set of all K automorphisms of L. So these are all the isomorphisms from L to itself that fix all of the elements of the base field K. And one of the things we proved early on about these Galois groups is that the size of for a finite extension, the size of the Galois group is always less than or equal to the degree of the extension. And if it's actually equal to the degree of the extension, then this is a special type of extension. And so we call this a Galois extension. Now, associated with Galois groups and subgroups of Galois groups are the fixed fields. So for a subgroup of a Galois group L over K, the fixed field of H is all of the elements of L that are fixed by all the elements of H, that are not moved at all by the elements of H. And one of the things that we proved about fixed fields is that if H is a subgroup of the Galois group of L over K, then L over the fixed field of H is always a Galois extension, where the Galois group is of L over the fixed field of H is equal to H. So when you pick a subgroup of the Galois group, look at its fixed field, that automatically gives you a Galois extension. L over that gives you a Galois extension. Then we started talking about splitting fields and normal extensions. Recall that if we have a polynomial f of x over a field L, then the splitting field for f of x over L is the smallest field such that f of x splits. So what that means is f of x factors into product of the linear factors, and for any other field that it splits completely in, this splitting field is going to be a subfield of it. So this is what we mean by the smallest one. Then for a normal extension, if an extension is normal, that means that if you take any irreducible polynomial, if that irreducible polynomial has one root in the upper field L, then that polynomial splits completely. So it has all of the roots in L. So any polynomial that has one root in L, all of the roots in L. Or alternatively, if A is in L, then all the other roots of the minimal polynomial for A over K are also going to be in L. And the big result we saw in this is that splitting fields are normal and normal extensions are splitting fields. So a finite field extension L over K is normal if and only if L is the splitting field for some polynomial over K. Okay, now we can get to the big guy, the fundamental theorem of Galois theory. So we're going to have L over K be a finite field extension where K and L are both subfields of the complex numbers. So first of all, L over K is Galois if and only if it is a normal extension. And this is something that we have already proved within the last week or so. We proved that one direction, that if it's normal, then it's Galois, and then you have a homework problem that's proving that if it's not normal, then it can't be Galois. And so that will give us our if and only if statement here. Furthermore, if you take an intermediate field between L and K, so this is saying that F is in between K and L, then the order of the Galois group of L over F is going to equal the degree of the extension of L over F, and the degree of F over K is going to equal, well, the order of the Galois group of L over K divided by the order of the Galois group of L over F. Okay, and so this tells us exactly the size of both the Galois groups and based on the degree of these extensions. So now we get to what is called the Galois correspondence. And what the Galois correspondence says is that there is a bijective inclusion reversing correspondence between the intermediate fields of a Galois extension L over K and the subfields of G, given by, if you have a field F, that gets mapped to the Galois group of L over F. And if you have a subgroup H of the Galois group of L over K, that gets mapped to the fixed field of H. And so this, the bijective means that there's, for each subgroup, there's exactly one corresponding subfield, and for each subfield, there's exactly one corresponding subgroup. The inclusion reversing, we've actually already proven that part. And so the inclusion reversing basically just says that if F1 is a subfield of F2, then that means that the Galois group of L over F2 is a subgroup of the Galois group of L over F1. And so the inclusion reversing is that we have swapped F1 is inside F2, but the Galois group for F2 is inside the Galois group for F1. And this is something that we proved early on with fixed fields. Alternatively, if you have that H1 is a subgroup of H2, which are subgroups of the Galois group of L over K, then the fixed field for H2 is going to be a subfield for the fixed field of H1. And so again, H1 is a subgroup of H2, and you end up with the fixed field for H2 being a subfield for the fixed field of H1. So that's the inclusion reversing part. Now, the last bits about the fundamental theorem of Galois theory is talking about when we have subfields that are normal extensions. And so an intermediate field N of a Galois extension L over K is normal over K if and only if the Galois group of L over N is a normal subgroup of the Galois group of L over K. And so the normal, where normal is coming from is the normal is talking about a normal extension is coming from a normal subgroup of the Galois group and vice versa. And so this normality is something that is preserved by this Galois correspondence. And finally, if an intermediate field N of a Galois extension L over K is normal over K, then the Galois group N over K is isomorphic to the quotient group of the Galois group of L over K modded out by the Galois group of L over N. Okay, so we're going to go through this and prove it bit by bit. We've done a lot of the heavy lifting already. Now it's just piecing things together. So we've already proven the first bullet that we did, saying that an extension is Galois if and only if it is normal. And so we're going to go straight to the second bullet, which is that if F is an intermediate field of a Galois extension L over K, then the size of the Galois group of L over F is equal to the degree of L over F, and the degree of F over K is equal to the order of the Galois group of L over K divided by the order of the Galois group of L over F. Okay, so if L over K is Galois, then it is normal. And one property of normal extensions is that for any intermediate field F, L is still going to be normal over F. So we automatically get that L over F is normal as well. And if L over F is normal, that means that it's Galois. So this implies that L over F is Galois, and so this gives us the first part of the statement, that the order of the Galois group of L over F is equal to the degree of L over F. Now for the second part, we're going to apply the Tower law. And so since we have that K is inside of F is inside of L, that means that the degree of L over K is equal to the product of the degree of L over F times the degree of F over K. Now we know that the degree of L over K is equal to the order of the Galois group of L over K, because L over K is Galois. And then since L over F is Galois, that means that the degree of L over F is equal to the size of the Galois group of L over F. So we can write that more nicely. And then to get our conclusion, we just divide by the size of the Galois group by L over F. And that gives us what we want. So this bullet is done. Now for the Galois correspondence part. So we're proving that there's a bijective inclusion reversing correspondence between the intermediate fields of a Galois extension L over K. We've already done the inclusion reversing part. And so we don't need to say more on that. We're going to focus on showing that this is a bijective correspondence. Okay? And so the way that we're going to show that this is a bijective correspondence is we're going to show that if you apply going from the field to the group back to the field, you have to end up where you started. And vice versa, if you start off with a subgroup to a field, back to a subgroup, you have to end up at the same subgroup. And that's enough to prove that this is bijective. So half of this we've already done. So we've already proven, and we had this up earlier on before, that if you're given some subgroup H of the Galois group L over K, then H is equal to the Galois group of L over F of H. And so how does this fit in with the bijection? Well, H is going to get mapped to the fixed field of H. And then that fixed field, when it gets mapped back through, going the other way, that's going to go to the Galois group of L over F of H by this correspondence. And then this gives us back H again. Okay, and so this tells us that this has to be a one-to-one map for H, because when you send it through and send it back, it has to get back to H, exactly to H again. Okay, now we have to prove it starting off at the field side. And so if we start off with some F, that's a subfield of L, that's in between, intermediate field between K and L. And we need to prove that this is the fixed field of the Galois group of L over F. Okay. And so note that we automatically have that F is a subfield of the fixed field of the Galois group of L over F, because F is fixed by all the elements of the Galois group. So F is automatically fixed by the definition of the Galois group, fixed by all else in the Galois group. So we don't need to say more about that. Now to get the other side of the inclusion, well, this means that we have F is inside the fixed field of the Galois group, which is a subfield of L. And so we can apply the Tower law. And so that's going to tell us that the degree of L over F is equal to the product of L over the fixed field times the degree of the fixed field over F. But we already know some degrees. So we know that L over F is Galois, and so that means that L over F is equal to the order of the Galois group of L over F. We also know, using the same theorem that we use for H, if we start with H equaling the Galois group of L over H, then we know that L over the fixed field of H is Galois, and so that means that the degree there also equals the degree of H, and so this is also Galois, the size of the Galois group of L over F. And so since those two are equal, that means that the degree of the extension of the fixed field of the Galois group of L over F has to equal 1. And we've proven that if you have a field extension of degree 1, then both fields must be equal. And so that finishes off this proof, showing the other way for the inclusion, for the bijection. Now on to talking about the normal extensions and the normal subgroups. So we're going to show that an intermediate field N of a Galois extension L over K is normal over K if and only if the Galois group of L over N is a normal subgroup of L over K. So for the forward direction, this actually was done through some homework problems. And so in those homework problems, we saw that there is a natural onto homomorphism we'll call phi that goes from the Galois group of L over K to the Galois group of N over K, where phi of some element of the Galois group sigma is sent to sigma restricted to N. And so this is where it's important that we're normal, because only for normal subgroups will this map be well defined. Will sigma restricted to N really be an automorphism on N? Then we saw that the kernel of this map is equal to the Galois group of L over N, and from what we've proved in Galois in group theory in abstract algebra 1 in the first semester, was that if you have a group homomorphism, the kernel of that homomorphism is automatically a normal subgroup. And so since we know that the kernel is the Galois group of L over N, that means that the Galois group of L over N is normal inside the Galois group of L over K. And so this is coming from kernels of homomorphisms are always normal subgroups. Okay, and so that gives us one direction. Now for the other direction, now we're starting with a normal subgroup of the Galois group of L over K, and we need to show that this gives us a normal extension. Okay, so we're going to let H be this normal subgroup of L over K, and so what we're trying to prove then is that we want to show that L over the fixed field of H is normal. That will give us our other direction here. And so let's start with some element A that's in the fixed field of H. Okay, and then let's suppose that B is another root of the minimal polynomial of A over K. what we want to show then is that B has to be in the fixed field of H as well. So if it has one root, A, then it has to have every other root. And we're just letting B be some other root. And if we can show that B has to be in the fixed field as well, then that's going to apply to all the roots of that minimal polynomial for A over K. And that's going to prove that we have a normal extension. So by the isomorphism extension theorem, we can take some element of the Galois group L over K that sends A to B. So we take some element sigma such that sigma of A is equal to B. Now let's take any element of H, of our normal subgroup. Let's call it tau. Then we would have that tau of B would be equal to the composition of tau of sigma of A, since B is equal to sigma of A. And then we're going to do sort of an old group theory trick. Well, we're going to apply sigma and its inverse to the left. So we're going to take tau of sigma of A and plug it into sigma inverse, and then plug it into sigma. Since sigma and sigma inverse cancel each other off, this gives us an equality. So here we are. Here it is again. And then what we're going to focus in on is this sigma inverse of tau of sigma. Okay. So we have sigma inverse of tau of sigma. Well, since H is normal, the definition of being a normal subgroup is that if you have anything, any tau in the group, and you have any sigma, you have any tau in this normal subgroup, and you have any sigma coming from the Galois group, well then sigma inverse composed with tau conversed with sigma is always going to land back in H. This is the definition of normal subgroup. So if you have forgotten the definition of normal subgroup, here it is, and this is why it's important. And so we know that this is inside of H. We know that this element sigma inverse of tau of sigma is inside of H. And so when we apply that to A, well, we're going to get A back because A is in the fixed field of H, right? And so all of this right here is equal to A, and so this whole thing is really just equal to sigma of A. And so we end up with tau of B is equal to sigma of A, but sigma of A, we chose sigma so that sigma of A is equal to B, and so we got that tau of B is equal to B. And so B is fixed by tau. Tau was an arbitrary element of H, and so that means that B is in the fixed field of H. Let's add in of H in there. And so this works for any other root B of the minimal polynomial for A, and so that means that all of the roots of the minimal polynomial of A are going to be inside that fixed field, and that's the definition of being a normal extension. And so that finishes off this direction and finishes off this bullet. Now to the final bullet. If an intermediate field N of a Galois extension L over K is normal over K, then the Galois group of N over K is isomorphic to the quotient group L over K over the Galois group of L over N. Okay, so this is the part that's a little bit funky because normally we wouldn't be able to get our hands on this Galois extension over here. Because if you think, if we have L, N, K, well, we can get the Galois group here. And automatically, if we take anything that's subfield and we do it up to the top field, we have our Galois group of L over N. Well, we have this natural relationship between these, that the Galois group of L over N is always going to be a subgroup of the Galois group of L over K. But we don't really have anything to talk about that part N over K. Well, what this is saying is that if we have a normal extension, then actually we can get our hands on this part of the extension too. And that part of extension is we're going to get it just by taking our large Galois group and modding out by what we just proved is a normal subgroup. So to prove this, we're going to go back to our onto homomorphism phi that sends elements of the Galois group of L over K to their restriction, to what they are restricted to N. The first isomorphism theorem for groups tells us that the image of this homomorphism is going to be isomorphic to the Galois group, to the domain, the Galois group of L over K, modded out by the kernel. Well, before we saw that the kernel is equal to the Galois group of L over N, and we know that this is an onto homomorphism, and so that means that the image is the Galois group of N over K. And so plugging that in, we get that the Galois group of N over K is isomorphic to the Galois group of L over K modded out by the Galois group of L over N. Exactly what we wanted. Okay, so we're going to conclude this video with one more result, which really shows the full fundamental theorem of Galois theory at work. And so this theorem, it's called in the literature the theorem of natural irrationalities. It's written up in a bunch of places. This was proven by Lagrange. I could not find a really clear reason why it's called the theorem of natural irrationalities. Also, in some places, it's called the base change theorem because it tells us how you can change the base fields in extensions. But let's just go through it. This is actually kind of an interesting and actually very useful theorem in telling us how we can extend what we know about one Galois extension to another Galois extension. And so the statement is we're going to start with a field K. This needs to be a subfield of C. And we're going to let N, which is equal to K adjoin alpha 1 through alpha of R, be a normal extension of K. Then we're going to take some other extension L, which is also a finite extension of K. And we need that the intersection between N and L, so these two extensions of K, the only subfield they have in common is K. And so their intersection N over L is equal to K. Then, if we take L and adjoin the same things that we adjoin to K to create N, so L adjoin alpha 1 through alpha R, look at that over L, then it is also going to be a Galois extension. It's also going to be a normal extension. And the Galois group for this extension is going to be isomorphic to the Galois group for N over K. So where is this kind of coming from? Well, this L adjoin alpha 1 through alpha R, this is the smallest extension that contains both L and N. And so there's actually, in the literature, there's a fancy name for it. It's called the compositum of L and N. And it's smallest in the sense that any field that contains both L and N will have to contain this field as well. So first we're going to show that this L adjoin alpha 1 through alpha R over L is a Galois extension, i.e. a normal extension, and we're going to do that by showing that it's a splitting field. So this is including splitting fields, connecting them with Galois extensions. Okay, and so if we let f sub I of x be the minimal polynomial of alpha 1, of alpha I, it should be alpha I, not alpha 1. Let's put that in black. So of one of these things adjoined to L, then we're going to define f of x to be the product of these minimal polynomials. So this is the product of the minimal polynomials. Our claim is that L adjoin alpha 1 through alpha r is the splitting field for this f of x over L. And this is why this is true. Well, so we know that n is a normal extension that contains all of the roots of f of x because they come from the minimal polynomials of the alpha i's over k. And so that means that f of x splits in n. N is a subfield of this L adjoin alpha 1 through alpha r by construction. And so that means that f of x is going to have to split here as well. So this L adjoin alpha 1 through alpha r, this is a field that it splits in. Furthermore, if we took any proper subfield f that was inside of L adjoin alpha 1 through alpha r that contains L, well, if it's not equal to L adjoin alpha 1 through alpha r, there must be some alpha I that's not in f. And if alpha I is not in f, then there's no possible way that f sub I can split in f. And since f sub I is a factor of f, that means that f of x can't split in f as well. So we have that it splits in L adjoin alpha 1 through alpha r, and it doesn't split in any smaller field. And so that tells us that it has to be the splitting field. So that gives us that this is a normal extension, i.e. a Galois extension, i.e. a splitting field. And so now let's finish up by showing that the Galois group of L adjoin alpha 1 through alpha r over L is isomorphic to the Galois group of n over k. Okay, and so finishing up the last part of the statement. We're going to do something similar to what we've already been talking about. We're going to create a map, we'll call it phi again, that maps from the Galois group from L adjoin alpha 1 through alpha r over L down to the Galois group of n over k. And this again is going to be defined, this phi is going to be defined just by you take your sigma in the Galois group up above and you restrict it down to n. So since n is a normal subgroup, that means that sigma restricted to n is an element of the Galois group of n over k. Since n is normal, it is a automorphism on it, and by design, since sigma fixes everything in L and k is a subfield of L, it's going to fix everything in k. So these are elements of the Galois group. These are k automorphisms of n. So this map is well defined. It's a group homomorphism because compositions of these maps are going to play well with the restriction to n, again, because n is normal. You're never, once you have an element of n, you're never going to be leaving n when you apply one of the elements of the Galois group to it. And so this is the homomorphism part. All you really have to show is that sigma of tau restricted to n is equal to sigma restricted to n of tau restricted to n. But again, because n is normal, the only way that you would be inside of, you'd have an element inside of here. The only way to get into n is if you were already in n. And so this line is that the homomorphism automatically works. Okay. And so now that we have a homomorphism, we can do our, simple trick of looking and figuring out what the kernel is and what the image is. So let's start with the kernel. Let's suppose that sigma is some element of the Galois group of this L adjoin alpha 1 through alpha r over L. And let's say that it's in the kernel. Well, if it's in the kernel, that means that when we restrict it to n, we get the identity. So that means that sigma of alpha I is equal to alpha I for each alpha I, because each alpha I is inside n, by construction. Furthermore, since this is in the Galois group of L adjoint alpha 1 through alpha I over L, well, that means that it fixes L. So sigma restricted to L is also the identity. And so putting these two things together means that sigma can only be the identity. The identity is the only element that does this. And so the reason is, well, what does it look like if you have some y in L adjoint alpha 1 through alpha r? Well, that means that y is equal to some sum of monomials. So L, call it Lj, times powers of alpha 1, let's say E1 comma j, to alpha r E r comma j, added together in some finite way. Well, if we apply sigma to this, we'd just be applying sigma to each of these pieces and sigma to this whole thing. Well, that's going to go back to our element of L because sigma doesn't change anything in L. And then this part right here is an element of N. And so since on elements of N it's the identity, it's going to give us back the same thing as well. And let's write it the right way. Summed up in the same way. And so applying this element, sigma doesn't change anything in L. This is for all y in our big field. And so this means that sigma has to be the identity. And so the kernel here is just the identity. So if the kernel is just the identity, that means that phi has to be 1-to-1. Finally, we're going to show that phi is an onto map. And so in doing this, recall that for any map like this, the image of the map is going to be a subgroup of the codomain. So it's going to be a subgroup of the Galois group of n over k. And now we're going to use our Galois correspondence. And so let's take some element beta of the fixed field of the image of phi. And so we're using our Galois correspondence here to go from the image of phi to the fixed field of the image of phi. And so since the image of phi, since this fixed field is going to be a subfield of n, that means that beta is going to be inside of n. So now let's think about what it means for beta to be in the fixed field of this image. So beta being in the fixed field of the image of phi means that phi of sigma of beta equals beta for all sigma in the Galois group. But phi of sigma, this really means that sigma restricted to n of beta is equal to beta. But since beta is in n, this just means that sigma of beta equals beta for all elements of the Galois group. And so we have that sigma of beta is fixed by all sigma in the Galois group of L of alpha 1 through alpha r over L. Well, that means that beta is in the fixed field of the Galois group of L over alpha 1 through alpha r over L. And by our Galois correspondence, that fixed field has to be just L. Since this is a Galois extension, the Galois group of L adjoint alpha 1 through alpha r over some subfield, the fixed field of that is always going to be just L. That is what the Galois correspondence is. So this is by the Galois correspondence. So we have that beta is inside both n and L, so it's in the intersection of n and L, and that means that beta is equal to k. So this implies that the fixed field of the image of phi is equal to k, but really it tells us that it's a subfield of k, but since k is fixed by all elements of the Galois group anyways, the other inclusion is automatic. And so we have the two inclusions, so this gives us equality. And so that means that the image of phi is equal to the Galois group of n over k. So phi is onto. And so now we know that phi is 1 to 1 and onto. And so that means that it is an isomorphism. And that tells us that our two groups here are isomorphic. Okay, so here is the statement of the theorem of natural irrationalities again. So an immediate consequence of this, the fact that the Galois groups are isomorphic, well, since the size of the Galois groups are equal to the degrees of the extensions, this automatically tells us that the degree of the extension of L of alpha 1 over alpha r is equal to the degree of the extension of n over k. And so if we draw this picture here, we have k here, n is normal over here, L some other extension, and there's no other subfields that contain that the intersection between n and L doesn't contain any other fields above k. And then you have this L adjoin alpha 1 through alpha r up here. And so what this theorem is really saying is that the Galois group talking about this piece, and so this is the Galois group over here, and the Galois group over here these two groups are isomorphic to each other. So these two, the Galois group talking about both of these extensions, these correspond to one another. And so a natural question is, well, how does this apply if the intersection is not just k? So what if the intersection between n and L is something larger than k? It has to be at least k because these are both extensions of k. But what if the intersection is some bigger field than k? Well, then at the end of the statement here, if you take that away, you can just replace it with that intersection. And the theorem will hold true. And the reason for that is that if n over k is normal Galois means the same thing, then that means that n over the intersection between n and L is Galois as well. Because it is a intermediate, because n intersect with L is an intermediate field, and any intermediate field is going to be Galois as L, and so the theorem directly applies again. So that is all for this monster video. I hope that it felt triumphant, and I will see you again soon.